perusal. All right. Organic Chemistry 2, Chemistry 3111. This is Chapter 16, Conjugated pi systems and pericyclic reactions. Everybody here knows what an alkene is. We spent a whole chapter talking about alkenes and alkene chemistry in Organic Chemistry 1. So if you have, just a double bond like this, we call that just a straight ahead alkene. But when they alternate, or when we have two double bonds in a molecule, we call that a diene. And we can have a diene when the pi bonds are adjacent to one another. We call that accumulated diene. Accumulated. When they're conjugated, what that means is that you have double bond, single bond, double bond, single bond. So they alternate back and forth, double, single, double, single. And those are going to be the most important ones for us in this chapter, are conjugated dienes. And there's a good reason why that is. And we'll talk about that throughout this chapter. And the last one are isolated. So just if you have, double bonds in your molecule somewhere, but they're not conjugated. So you see it goes double bond, then it goes single, single, right? So that's not conjugated. So we call those isolated double bonds, or we call that an isolated diene. So these are the three classes of dienes. Obviously, you have to be able to recognize them, and you can see how they would lend themselves to a multiple choice question very easily. Is this conjugated? Is this cumulated? Is this isolated? Well, if we look at a conjugated diene, okay, and if we look at one really closely here, if we look at the orbitals, I should say, of a diene, in a conjugated diene, we'll start there. You can see that in a conjugated diene, and that's what's being represented here, is you have the double bond, single bond, double bond, like this. Remember, each one of these sp2 hybridized carbons has a p orbital on it, and that's what's drawn here, a lot better than I can do here. But what you see is that they completely overlap, right? They form that conduit, so the pi electrons are delocalized throughout the entire molecule. Whereas if we look at the cumulated, you can see that the pi bonds are actually perpendicular to each other here on this carbon that has both double bonds on it. And so there is no conduit, or there is no orbital overlap here. And so the electrons are not all delocalized. And in the isolated, well, it's just like it says. The double bonds are totally isolated. So the only one where we have overlap of all the p orbitals in a continuous system are in conjugated dienes. Now, the conjugation in double bonds doesn't necessarily have to just involve carbon-carbon double bonds. And we've seen that throughout Organic Chemistry 1 and a little bit in Organic Chemistry 2. So this chapter, Chapter 16, focuses on the conjugated systems. So we're going to talk mostly about conjugated systems and the special properties and reactivity that are associated with them. And we're going to talk about why they have special properties and special reactivity. Now, like I was alluding to just a few seconds ago, a conjugated system can have a heteroatom in it. So that means, what's a heteroatom? It could have an oxygen, a sulfur, a nitrogen, let's say, in it. So a carbonyl has a double bond, and that can count as part of a conjugated system, right? We have double bond, single bond, double bond. So here we have a beautiful conjugated system, and we call that an enone. And you can guess where that word comes from. Alkene, right? And then ketone, right? You put those together, we have an ene and an one, and we call it an enone. Not a joke, right? Here's another example of a fully conjugated system, or not completely conjugated, but you see how we have double, single, double, single, double, single, double. So everything that I have highlighted in blue is all part of a conjugated system. So I could circle all of this here and say all of this system is conjugated. Okay, so conjugated. Whereas this double bond over here is not conjugated to anything. Why? Because you notice that that double bond is isolated. It's by itself, right? You have single, single. You have to, in order to have a conjugated system, it's got to go double, single, double, single. So this would be isolated, okay? By itself, all alone, not conjugated. Well, with that in mind, let's take a look at some interesting compounds here, and we're going to decide whether the carbon-carbon pi system is cumulated, conjugated, or isolated. We'll start with cis aconitic acid, which you probably remember from the citric acid cycle. If you've ever studied biology, you might have heard of the enzyme aconitase, right? It's a very common enzyme that comes up when you're discussing the Krebs cycle, or the tricarboxylic acid cycle, whatever you want to call it. Anyhow, if I was to, let's say, circle, I'll use my yellow pen. It doesn't get a lot of love. If I was to circle all of these double bonds here, how would you describe that? Would you say that's cumulated, isolated, or conjugated? What I have in the yellow circle. Yeah, those are conjugated, right? Because it goes double, single, double, single, double. So these are conjugated. Now, there is another double bond in the molecule that is not conjugated to the system. How would I describe that one? It's isolated. Isolated. There you go. All right, so if we move on to B, it says osamine present in essential oils of many plants. I had a student a number of years ago. I got injured. Anyhow, I got cut, and one of my students was obsessed with essential oils. So she brought me some essential oils to put on my hand where I got cut. Anyhow, so here we have an essential oil, or a compound that's present in many essential oils. And you can see that right here we have a couple of double bonds that are conjugated, right? Because they alternate, double, single. And then I have one over here by itself, right? Because it's separated by 2 sigma bonds before you get to the next pi bond. And so it is isolated. There we go. And then we have one more. So this is Cis Jasmine, a constituent of many perfumes. And you can see there is a conjugated system in here, right? If you circle, let me use the blue pen. If you circle these 2 double bonds, these are conjugated, aren't they? Conjugated. But there's another double bond in here that is isolated. This one right here is not conjugated. Why? Because you have 2 sigma bonds before you get to the next pi bond. So it is, in fact, isolated. Now, I'm hoping that you find this pretty, and again, I never like to use the word simple in organic chemistry, but I'm going to say it's simpler than some of the concepts that we've looked at in this class. Give me a thumbs up if you follow me on the concept of cumulated, isolated, and conjugated. Yeah, okay, good. Well, another thing I want to mention about cumulated alkenes. So if you have something like this, right, there's another name that we use for these, and I don't know if it comes up in our class a whole lot, but sometimes these are called allenes. So an allene, anyhow, or allene, or an allene, allenes. It's a functional group that you can know, which is a brand new one, which is kind of cool. It's always fun to learn a new functional group. You know. Well, let's move on and take a look at how would you make a conjugated diene. Well, good news is that our book doesn't go into a ton of detail about ways that you would make a conjugated diene. So one way that you would do it is, let's say you had this molecule right here, right? And you were to treat that with potassium T-butoxide, which is a hindered base, right? So what would that do? Let me draw the structure of potassium T-butoxide. We'll leave the potassium out. But here's your butoxide. You've got a beta proton right here. Maybe I'll draw it pointing down like this, right? And then the base would just pluck. The base would just pull that proton off in an E2 reaction to make a conjugated diene. Another option, and this is a real hammer and tongs approach, but it would work, is if you had this vicinal 1,2-dibromo and you treated it with excess T-butoxide, you would just do an elimination of one of these protons and then one of these protons, right? And you would end up making 2 double bonds. So that's really the only method, I think, that our textbook goes into with respect to synthesis of dienes, or just using hindered bases on these vicinal dibromides, or a bromide where you have a double bond next to it like that. Let's move on from there and let's talk about the bond lengths in a conjugated diene. So if you look at the bond length in a molecule like ethane, this is just plain old ethane here. If you look at the carbon-carbon bond length, it's around 153 picometers. Now, both of those carbons are sp3 hybridized, right? But if you look at the carbon-carbon bond length, it's still a single bond, right? Both of these bonds are single bonds, okay? But if you look at it in this molecule, which is called 1,3-butadiene, okay, right? You have 1, 2, 3, 4. So you have a double bond on carbon 1, a double bond on carbon 3. So 1 and 3, buta, because there's 4 carbons total, diene, because it's a diene. So 1,3-butadiene. That molecule is going to come up a heck of a lot in this chapter, so you should know the name of it. But again, going back to that single bond in 1,3-butadiene, it's shorter, right? It's shorter by a little bit. Now, why is that? Well, it can be partly, not completely, but it can be partly explained by the hybridization of the carbons involved in that sigma bond, right? Both of the carbons in here, right? Both of those are sp3 hybridized, whereas both of these carbons in this single bond are both sp2 hybridized. And if we think about what is an sp3 orbital, hybrid orbital made of, made from, 1s and 3 p's, or it's 25% s, 75% p. What's an sp2 orbital? Well, it's a hybrid orbital that's 33% s and 66 or whatever, 66.6% p, neither here nor there. But the idea is that since an sp2 orbital has more s character, and s orbitals are smaller than p orbitals, then it's just going to be a shorter bond. Okay. Now we can also partially explain this, or kind of round it out using molecular orbital theory, which we're going to look at very briefly in a few minutes. So there we go. Conjugated dienes. Again, the carbon-carbon sigma bond is shorter than a regular carbon-carbon single bond. Why? Because of the hybridization of the carbon atoms involved in that bond. What else here? It says the heats of hydrogenation show that conjugated dienes are actually more stable. Now, what's going on in this picture right here is, let's say you had 2 molecules of 1-butene, right? That's what's being shown here. This is 1-butene. And let's say you had 1 molecule, so this is 2 molecules. So we can put 2 times 1-butadiene, or this is 1 molecule of 1,3-butadiene. So what they're comparing is the heat of hydrogenation of 2 double bonds in 2 different molecules, or 2 double bonds in the same molecule. So 2 double bonds in the same molecule. So presumably they should release the same amount of heat, because either way, all you're doing is hydrogenating 2 double bonds. Okay, but you notice that the amount of heat released upon the hydrogenation of 1,3-butadiene is less. It only releases 239 kilojoules per mole of energy compared to 254. So what is that? That's a difference of 15 kilojoules per mole. So that means that, if you're wondering, like, what's the take-home message here? The take-home message is that the 1,3-butadiene molecule is more stable than the 1-butene, and you compare the two, and the amount of stabilization is 15 kilojoules per mole. And so where does that stabilization come from? It comes from the conjugation of the system. So a conjugated system is more stable, okay, than, or conjugated dienes are more stable than isolated double bonds. So that's kind of interesting, a very interesting experiment too. So if we had all of these compounds here, you can see there's a bunch of double bonds in all of these compounds. It says to rank them in terms of their increasing stability. So we're going to start with, let's start with least stable, and then we'll go all the way up to most stable. Now I have a note here written for myself that students usually find it easiest to identify the most stable compound first. Could anybody tell me which one of these would be the most stable compound? So we'll start with the most. Which one of these would be most stable? Yeah, D is going to be the most stable. Absolutely. So, Courtney, Skylar, you're both 100% correct. All right. It's because it's fully conjugated, right? Double, single, double, completely conjugated. And so the most stable is going to be D, right? This is called fully conjugated. Now, could anybody tell me which one of these would be the least stable based on your prowess. Yes, I agree, Skylar. The least stable is going to be A. Right? A is going to be the least stable. Why? Because both double bonds, right? Both are isolated. Okay. Now I saved B and C for the end, and there's a reason why, because I think these ones are a little trickier. If you look at B, I'll use the blue pen, you can see that you have a fully conjugated system right here, right? And then you have an isolated double bond here. If you go over to C, you've got two double bonds that are conjugated, and then you have one that's isolated. I'm going to throw this out there to my students. In terms of B and C, could you tell me which one do you think might be more stable? And it's not a trick question. It's not to try to trip you up or anything. Question's not to try to make your life miserable or anything. Yeah. Okay. Jenna she is guessing C. Does anybody else have another guess? And this one might not be abundantly clear. Think back to Organic Chemistry 1 and the stability of double bonds, right? Because if we look at the isolated double bond in both of these, right, that alkene is disubstituted in both cases, right? Both of those are disubstituted. We could write a note, say this is disubstituted and this is disubstituted, so disubstituted, okay? Now if we focus on the conjugated systems, right, and I'll kind of go over them quickly. Here we have a disubstituted, and then we have a tri-substituted alkene, so we could even put di and tri. Here we have a tetra-substituted, tetra, and here we have a tri-substituted. Now remember from Organic Chemistry 1 that the more substitution we have in a double bond, the more stable it is. So since B has more substitution on the two double bonds, B is going to be more stable, and then C will be in between B and A. So it goes from D is the most stable, B is the second most, C is the third most, and A is the least stable of all. Give me a thumbs up if you follow me on the concept after I kind of gave you the run through. Right? And this kind of goes back to Organic Chemistry Organic Chemistry 1 a little bit. It might be something that might escape your memory a little bit, but I'll just kind of review it with you here. If you remember alkenes, right? When you went from tetra-substituted, they were the most stable, right? And that was more stable than a tri-substituted, which is more stable than a di-substituted, and di-substituted can be like this, or, you know, like this, and then that's more stable than a mono-substituted. Okay, so that's the stability of an alkene. So something to keep in mind when you're looking at the relative stability of any kind of system that has double bonds in it. All right, let's get back to that whole concept of conjugated dienes. It says generally sigma bonds will freely rotate. Let's say we had our molecule here, our famous molecule. This is just 1,3-butadiene. Again, it's going to come up a lot in this chapter. That sigma bond, this sigma bond right here, this is a sigma, and that's the bond right there. It's actually got two most stable rotational conformations, what we call an S-cis and an S-trans. The S stands for sigma, okay, right, because it's a sigma bond, and there's free rotation around that bond. It says the p orbitals are conjugated only in these two rotamers. Right, we call them rotamers because they're conformers that result by the result of the rotation of a sigma bond. Well, let's take a look at the relative energy of these two rotamers. Okay, the S trans is going to be lower in energy. Right, this is the S trans. It is lower than energy or lower in energy than the S cis. Right, because these two methylenes are farther away from each other, right? If you were to look down the Newman projection of this, what would you see? You would see a double bond to a CH2 up here, right? And you would see a double bond to a CH2 down here like this, right? They're far away from each other. I'll just erase that. But you can see that in the S-cis conformation that the double bonds are eclipsing each other, okay? And then in order to rotate this sigma bond, you have to increase You have to bypass or go over an energy barrier of 15 kilojoules per mole. And the reason why it's so high is because once you get up to this 15 kilojoules per mole, there is no overlap of the p orbitals, right? Remember, in the S-cis, you have complete overlap of all 4 p orbitals. In the S-trans, you have complete overlap of all 4 p orbitals. But when you rotate it, you go through something that doesn't have overlap of the p orbitals, right? And if you're wondering what that looks like, well, I have a picture of it right here. The highest energy conformer is not conjugated at all, and therefore it is 15 kilojoules per mole less stable. I have a little model here that I can show you quickly. So let me just stop presenting. Come on. Go. If I use my camera. So this is a molecule, this is a model of 1,3-butadiene right here. So you can see I've got double bond here, single bond, then another double bond. So this would be the S-trans, or the S-trans, 1,3-butadiene, right? I have free rotation. This is the S-cis. So, right, you look down like this. There, the two methylenes are eclipsing each other. Then I'm going to make the S-trans. They're anti to each other like this. But the whole idea is this. You go from S-trans to S-cis. So there's free rotation around that carbon-carbon bond. So you start with the S-cis, which is down here. Then as you rotate that bond and it's perpendicular, you rise up really high in energy, right? Because you don't have total overlap of the p orbitals. Then you come down to the S-trans, which is even more stable, right? Because you have that continuously overlapping system of p orbitals, but these two groups are farther away from each other. So to review, you start with the S-cis, really high in energy when they're perpendicular, and then you go down to the S-trans, which is the most stable, like that. All right, so let me go back here. Okay, hopefully you found that demonstration a little bit helpful. Nope, that's the wrong chapter, Mr. Dion. There we go, chapter 16. Okay, so there we go. Now, in terms of the bond length in 1,3-butadiene, right, and this is something that we talked about just a few minutes ago. We said that when you have that molecule, 1,3-butadiene, this guy right here, we said that the bond length was around 148 picometers, as opposed to the bond length in ethane, which is around, greater than 150 picometers. Right? Now, why was that? Well, we said that it could be partially explained by the hybridization of the carbons, that both of these are sp2, whereas these are both sp3 hybridized. But we can also explain it using molecular orbital theory. Now, I don't focus a lot on MO theory or molecular orbital theory in Organic Chemistry 1 or Organic Chemistry 2, but I just want to show you quickly how we can use it to also partially explain that shortened bond length in the sigma bond of 1,3-butadiene. So just a review of molecular orbital theory. If we have the molecule ethylene, and this is the molecular orbitals shown for the double bonds or the pi bonds of ethylene. So we have just an ethylene molecule. Son of a gun. What am I drawing? So if we have ethylene, which is just this. If you have a question, feel free to unmute your mic.
Yeah, your screen is not shared.
Oh, shoot. Sugar. I thought I shared it. There we go. Boo, boo. There we go. So let's go back. Take a step back. Right here. So this is where we left off, kind of was talking about the conjugated diene. I guess this is the last thing you could probably see, or something close to it, right? Where we have 1,3-butadiene, and I was talking about the bond length and saying how when we have 1,3-butadiene, the sigma bond is shorter than the sigma bond in ethane, and I said it could be partially explained by hybridization, right? The two carbons here are sp2 hybridized, where the two carbons here are sp3 hybridized. But what I was getting at is that in 16.3, we use molecular orbital theory, or MO theory, to explain why, to also partially explain, rather, why the double bond is shorter. Okay, so just a little bit of a review. Let's say we have ethylene, and you know that there's a pi bond in ethylene. Well, what's that pi bond made of? it's made of the overlap of two p orbitals, right? So two atomic orbitals, two p orbitals. And for every atomic orbital that we have, we can create a molecular orbital. So since I have two p orbitals, right? Two atomic p orbitals in the pi bond of ethylene, I can make two molecular orbitals. I'm going to have one that's a bonding molecular orbital and another one that's an anti-bonding molecular orbital. The bonding molecular orbital will be lower in energy than the anti-bonding molecular orbital. Remember that each p orbital has one electron in it, okay? And according to the Aufbau principle, both of those electrons are going to go into the bonding molecular orbital, right? Because I can hold two electrons in every orbital. So there they are. Both of them are in there. So if I further this to 1,3-butadiene, here are the rules. Now we've got 4 atomic orbitals. So we're going to form a total of 4 molecular orbitals. Now, in terms of the number of nodes or regions where there is no electron density, we always start with 0 and we build our way up from there. So 0, 1, 2, 3 nodes, right? Remember that each one of these p orbitals brings in 1 electron, and we can hold a total of 2 electrons in every molecular orbital. So I have the molecular orbitals, they're called psi1, psi2, psi3, psi4, which is neither here nor there, really. But the idea is that all 4 of those electrons, since I can put 2 in the first one, the lowest energy molecular orbital, and 2 in the second lowest energy molecular orbital, that all of the electrons are in these 2 molecular orbitals. If we just focus in on those, and we just don't even worry about these right now, if we just focus in on those first 2, you notice that in the lowest energy molecular orbital, those two carbons have pi bond character, right? Because there's overlap of the p orbitals, right? Again, what we're talking about here is 1,3-butadiene, right? So in this molecular orbital, you see that there's pi bond character in that in that bond. Whereas here we have a node, and that represents, a region of no electron density, right? We have the pi bond here and the pi bond over here. But again, what's the take-home message? The take-home message is that this bond has some double bond character, and it also has some single bond character. So a double bond is shorter than a single bond. Therefore, since that bond that I have highlighted in green has a little bit of both of those characters, it explains why it is shorter than a regular sigma bond. So that's using molecular orbital theory. Now, in terms of the rest of the section about molecular orbital theory, and this is the explanation right here, I want you to be sure to read the section on MO theory. We're not going to cover all of the sections in this book that deal with MO theory and different reactions, but it would be wise for you to read the remainder of this section. And here it's showing all the molecular orbitals for 1,3,5 hexatriene. So if we have 6 carbons, we have 1, 3, 5 hexatriene. We have a total of 3 atomic orbitals, right? 3 p orbitals on every carbon in here. So if we have, sorry, did I say 3 when I meant 6? We have a total of 6 p orbitals, right? We have 6 p orbitals. So how many molecular orbitals can we form? 6. How many nodes are we going to have? We start with 0 nodes, then we go to 1, 2, 3, 4, 5 nodes. And that's what you can see in all of these molecular orbitals. If we have a total of 6 p orbitals, how many electrons do we have? 6 electrons. If we can fit 2 electrons in each orbital, where are they going to be? They're going to be in these 3 orbitals here, the ones with 0, 1, and 2 nodes, like that. All right, so that's just a little bit about molecular orbital theory. The molecular orbitals that are of greatest interest to organic chemists are the highest occupied molecular orbital. We call that the HOMO. That's the highest energy molecular orbital that has electrons in it. And then the LUMO represents the lowest unoccupied molecular orbital. So the lowest energy one that has no electrons in it, because this is kind of where the magic happens, so to speak, when we look at reactions that involve molecular orbitals. And we call these, the HOMO and the LUMO, we call those the frontier orbitals. All right, well, again, really the take-home message from section 16.3, the main thing that you need to know, and I don't like rifling through my slides too much, But the main thing that you need to know is what's shown here, okay? It's just another way to explain why the sigma bond in 1,3-butadiene is shorter than you would anticipate if it was just made from sp3 hybrid orbitals. All right, let's move on to electrophilic addition. And we're going to get back into some arrow pushing here, right? Getting at the old curved arrows. Remember that in section 9.3, so way back in the day, okay, in Organic Chemistry 1, you learned about the addition of a halo acid like HBr or HCl or HI to a carbon-carbon double bond via Markovnikov addition. So the first step is a proton transfer, and then we get a nucleophilic attack. Well, what would happen if you tried to treat 1,3-butadiene with HBr? Right, what's going to happen then? Well, what you actually end up with is a mixture of products, okay? You end up with this mixture. I mean, the first one, you can see the double bond hasn't moved, but you see that in this product here, you have the double bond moved over there. So how did that happen? Okay, well, in order to determine how that happened, the easiest way to do it is to look at the mechanism. So let's take a look. What happens when you do the protonation? The first step, remember, the rich get richer, right? If we draw on this carbon has 2 vinylic protons, this only has 1. So this is the carbon that's going to take the proton. Therefore, this is the carbon that's going to end up with the positive charge, the carbocation. If we draw that carbocation, what do you see? It's allylic. Therefore, it's going to have a resonance contributor, which means I have 2 different carbocations. I have this one and this one. Now, my nucleophile, okay, my bromide, it could do the nucleophilic attack, and this is me adding too many curved arrows, but it could either attack here or here, okay? And we're going to see that in a few seconds. So you could do a nucleophilic attack at either of those carbocations. Now notice that the primary carbocation is not going to form, okay? We're not going to do anti-Markovnikov addition. We're not going to start whipping up primary carbocations because they're highly unstable. Well, again, this is showing what I was just trying to represent, that you end up with these 2 different carbocations, and the bromide can come in and attack that positive charge or that positive center, and you end up with 2 different products, one that we call the product of the 1,2 addition, and the other one we call it the product of the 1,4 addition. Where do those numbers come from? If you number the compound, you've got 1, 2, 3, 4. The product of 1,2 addition has the hydrogen on carbon number 1 and the bromine on carbon number 2. The product of the 1,4 addition has the hydrogen on carbon 1 and the bromine, you can see, is on carbon 4. So that's where those words come from. And sometimes we call this one, we'll call this one the 1,2 adduct. We'll call this one the 1,4 adduct. And that's probably the word you're going to hear me use, is the 1,4 adduct and the old 1,2 adduct and the 1,4 adduct. All right. Well, with that in mind, what would happen if you were to just treat that 1,3-butadiene molecule with just bromine? Right. Well, then it's going to proceed through a bromonium ion, and you're going to end up getting both the 1,4 adduct and the 1,2 adduct as well. All right. And so this is a reaction that I could ask you, on your next quiz, even though we're largely going to focus on adding halo acids to conjugated systems. So with that in mind, let's take a look at a practice problem. This is question 16.6 from your textbook. This is a really good question. I think this is one of the, excellent question. And it's not an easy question. Okay, we're going to need this entire space just to solve the first one, just to solve B. So we're going to start with that. And then after that, we'll go to a blank PDF and we'll try problem C. All right, so what's going to happen here? First, I need to redraw my HCl molecule like this. Well, let's just start over here. Okay, let's start with this double bond, and let's do a, Markovnikov addition, right? So the rich are going to get richer. Well, if I look at the double bond here, okay, it's tetrasubstituted. So which one of these carbons is going to take the proton? if I put the proton here, I end up with a carbocation here, which isn't resonance stabilized. However, if I add the proton here, then I would end up with a carbocation here that would be resonance stabilized. So that means the proton is going to go on this carbon, and we're going to get an intermediate that looks like this. So we'll have these two carbons, I have this guy, and I have, so remember, I added the hydrogen here, okay? So now I've got a positive charge right here. But that's an allylic carbocation, so we could draw a resonance contributor for that. So let's do that. And let's draw the curved arrow like this. We would end up with something that looks like this. We've got a double bond here. Okay, and now we're going to have a positive charge over here. So we've got two different carbocations. Well, what does that mean? That means that the bromide could attack at either one of those positions, or sorry, the HCl. So the chloride could attack at either one of those positions. So I'm going to draw my chloride, and I'll draw it here, chloride, and I'm going to use the green to represent the nucleophilic attack. So I could either do a nucleophilic attack here, or I could do a nucleophilic attack here. Notice that I'm kind of drawing two arrows on the same thing. So I'll just leave the green arrow out here because I don't like to have two different arrows that represent two different things on the same molecule. It's kind of ugly. So let's draw what we would get here. We would get something that looks like this. We have these two methyls. Yeah, oops, that's not very pretty, is it? We have a methyl group here. We have a chlorine here. And then we have this geminal dimethyl here. Remember that this is going to be racemic. So we could write here racemic, because this is a stereocenter, and that chlorine can come in and attack from either face of the molecule. Why? Because the carbocation is sp2 hybridized. If we draw the product of the nucleophilic attack here, we have these two carbons, we have this double bond, methyl, these two carbons, and then we have the chloride would attack over here, so we end up with this molecule as well. The thing is, we're not done. Okay, we're not done yet, because this is not a symmetrical alkene. Now we need to do the same thing, and we need to do it over here. So again, instead of using Markovnikov, okay, in terms of our HCl addition, we want to add the hydrogen so that we end up with an allylic carbocation. So if I was to do the addition over here, I'm going to draw a second molecule of HCl. Again, there's a lot of work here involved, and I'm really going through everything in detail. I'm going to use a green arrow to represent the proton transfer. And from that proton transfer, I'm going to draw it down here. What you would get would be something that looks like this. So you added the green proton. You added the green proton right here. Okay. Then you would end up with something that looks like this. You'd have the positive charge here, and then you have the double bond here, and then something that looks like that. But this is also resonance stabilized, isn't it? Right? This is an allylic carbocation. So we can draw the pi bond moving over here, and then we're going to end up with a tertiary carbocation. So let's draw that resonance structure. It's going to look like this. We have a double bond here, these two methyls, and we have a positive charge here. Okay, now you can see how very quickly I ran out of room on this, but if you draw product of the nucleophilic attack here, you end up with this molecule. Son of a gun, I'm really running out of space here, aren't I? But you end up with the chlorine here, and then if you do the same thing here, you end up with this guy. Did I miss a methyl group? I did, and nobody stopped me. There you go. And you end up with this guy that looks like that. And so we end up with a total of 4 different molecules. Keep in mind that this one is racemic too. I forgot to point that out. So we end up with 1, 2, 3, 4 different products in this case. All right, so what did we do? We drew the product, or the allylic carbocation that resulted from the addition of HCl on this double bond and on this double bond. We drew the resonance contributors both times, and then we drew the product of nucleophilic attack, and we ended up with a total of 4 compounds. 2 of them are racemic mixtures, and 2 of them don't have a chiral center. Did I forget another carbon down here? I did. There we go, like that. All right, well, with that in mind, let's try C, and let's get a big blank sheet of paper here so that we have enough room to solve this thing. These things take a lot of space. I mean, once you get the hang of it, it's just kind of the same thing over and over, but you do need adequate workspace to do it. So this is 16.6. Which one is this? Is this C? Yeah, 16.6 C in your textbook. 16.6 C. All right, so we've got this cyclic compound that's a diene. We've got geminal dimethyl here, and we're going to treat this with HBr. Okay, let's start with this double bond over here. Okay, we're going to have to do the proton transfer over here in order to form an allylic carbocation. So let's draw what that allylic carbocation looks like. We have our double bond here, single bond here. Our carbocation is right here, and let's draw the resonance contributor for it. So when we draw the resonance contributor, the curved arrow is going to look like this. We're going to have the double bond here. We're going to have our positive charge here. We've got a methyl here, and we've got the gem dimethyl like that. Okay, I'm going to delete the resonance, the flow of the electrons for the resonance, just because I want to use these structures and I want to draw the nucleophilic attack that's going to occur. So I have my bromide here. I have bromide here. Bromide could do a nucleophilic attack on this carbon, and bromide could do a nucleophilic attack on this carbon. Let's draw what those products would look like. The first product will look like this. I have my gem dimethyl. I have the bromine over here like that. And that's going to be a racemic mixture. Racemic. Why? Because this is a stereocenter. And this is an sp2 hybridized carbocation. Therefore, the bromide could attack from either face of the molecule. With the next one, let's draw what the product would look like. I have my double bond here, single bond, gem dimethyl, and I have my bromine over here like that. There we go. And this compound is also racemic. Now what we're going to do is we're going to take this same molecule. So let's start over. So I'll copy this. Okay, and I'm going to move down here. And I'm going to paste it here. Now we're going to delete these curved arrows, and we're going to do the proton transfer on the other carbon, on the other carbon. So we're going to do something that looks like this. Okay, and then we're going to form this carbocation. So we end up with this. We have our gem dimethyl. We have our pi bond here, and our carbocation is here. This is resonance stabilized, right? It's an allylic carbocation. So we can draw a curved arrow like this, and then that's going to give us this resonance contributor. We have the single bond here, like that. And now our positive charge is up here. Just like before, I'm going to delete the resonance arrow because I want to use both of these to show the nucleophilic attack. So I can take the bromide and do a nucleophilic attack here, take the bromide and do a nucleophilic attack there. So if I draw the curved arrow for the nucleophilic attack, it could attack here, or it can attack here. Then if I draw the products that result, I'm going to make this guy, double bond here, the bromine here. Again, where the bromine attacked, it's a stereocenter, so this is going to be racemic. And where the bromine attacked here, I'm also going to form another chiral center right here. And this is also going to be racemic. And so we ended up with a total of 4 compounds. Compound 1 that was a racemic mixture. Compound 2, that's a racemic mixture. 3 is a racemic mixture, and this one is also a racemic mixture. And so what did we do? The same thing that we did in the first problem, where we added the HBr to one of the double bonds. We drew both of the resonance contributors of the allylic carbocation that resulted, this one and this one. And then we drew the nucleophilic attack on both. Then we drew the addition of HBr to the other pi bond to make an allylic carbocation. We drew both resonance contributors, and we drew the nucleophilic attack to both, and we came up with those 4 compounds. Give me a thumbs up if you follow me on just the rationale for the problem. You know, you understand, like I understand, if you understand what's going on, okay? Would I expect you to nail this immediately after seeing it one time? Probably not. I think it's one of those things that you would want to review by yourself. So when it says racemic amounts, I'm not sure what a racemic amount means. Would they be 50-50 mixtures? Yeah, when it's racemic, it would be 50-50. Yeah, presumably it would be 50-50. Right? The only time we can form new stereocenters and they're not formed in 50-50 mixtures is when we make diastereomers. In that case, sorry, go ahead.
Oh yeah, I'm sorry. I was asking more about the products, not the stereocenters. Like, is there any favoritism for any, like,
no,
bond?
Our book doesn't cover anything about which one of these would be a major product or a minor product. No.
Okay.
Not for this question. However, we will look at a 1,2 and a 1,4 adduct and talk about ways to favor it or to favor the formation of one over the other.
Okay.
All right. So with that in mind, let's move on to that subject. So there we go. Now, I told you what a 1,2 adduct and a 1,4 adduct is. We went over that, I don't know, maybe 10, 15 minutes ago or something like that. But the ratio of 1,2 versus 1,4 addition to form those 1,2 and 1,4 adducts depends on the temperature. You see that at cooler temperatures, like 0 degrees Celsius, the 1,2 adduct is going to predominate, whereas at warmer temperatures, like 40 degrees Celsius, the 1,4 adduct is going to predominate. The reason why can be explained when you take a look at the reaction pathway and the energy of the intermediates that are formed. So if we take a look at the first step, the proton transfer is the same for both. We make a carbocation. And then when we do the nucleophilic attack, if we make the 1,2 adduct, we end up with a product that is higher in energy. And when we do the 1,4 adduct, we make a product that is lower in energy or more stable. Why would the 1,4 adduct be more stable than the 1,2 adduct? Well, I can tell you that here, the reason why is because this alkene is di-substituted, whereas this alkene here is only monosubstituted. Monosubstitution versus di-substitution. So the 1,4 adduct is going to be thermodynamically favored. And so we call the 1,2 adduct, oftentimes we call it the kinetic product because it forms faster. Its energy of activation is a little bit lower. And we call the 1,4 adduct the thermodynamic adduct or the thermodynamic product. Why? Because it's more stable. All right. So stability or thermodynamics versus kinetics. So when we're looking at kinetics, which one's going to be faster? It's going to be the 1,2 adduct. But which one is going to be more stable in the long run? Well, it's going to be the 1,4 adduct. All right. Now, if we think about the difference in the activation energies for the nucleophilic attack, I'm not sure if our textbook goes into this or not, but I think it's worth looking at. If you look at the nucleophilic attack that's occurring here that leads to the 1,2 adduct, the carbocation is secondary allylic, Okay, it's exactly this one right here. But if you do the nucleophilic attack that results on the, to give you the 1,4 adduct, the intermediate is primary allylic. It's actually this. So it's primary allylic, this one here, primary allylic, which is going to be higher in energy, right? It's resonance stabilized, but it's still primary. Anyhow, so that's the difference here. And again, I don't even know if our textbook goes into that, but just to give you some rationale for that. There you go. So again, the 1,4 adduct is more stable. I just explained why. It's simply because it's more substituted, nothing more than that. So again, and when we have a higher temperature, there's going to be an equilibrium, right? If you jack the temperature up high enough, right? If you jack it up, well, then you're going to end up forming both of these, right? And it's going to go back and forth and back and forth. There's going to be an equilibrium if you're at a really high temperature that's higher than both of these activation energies. But which one's going to end up resulting is thermodynamics is just going to drive the formation of the 1,4 adduct. You're going to get the more stable product. And we call that thermodynamic control, right? Thermodynamic control. Whereas the 1,2 adduct presumably forms faster at low temperatures, right? Because of a proximity effect, because the carbocation is simply closer to where the proton transfer actually occurred. Okay, we call that kinetic control when we do the reaction at a lower temperature. So kinetic control, low temperature, 1,2 adducts, thermodynamic control, higher temperature, 1,4 adducts. Okay, so those are things that you've got to know for the next quiz and moving forward. So you can see that I get a couple of beautiful examples here in question 16.9. And it says, predict the products for each of the following reactions. In each case, determine which product will predominate. Now, unlike those last problems that we looked at where we formed, 4 different products, since these two alkenes in both of these questions, since they're both perfectly symmetrical, right? They both have a plane of symmetry in them. You're only going to end up with 2 products for each of them, right? 2 products for this one and 2 products for this one. So you get a 1,4 adduct and a 1,2 adduct. And what I want to do now is take a break and we'll pause the video and the recording. And then when we come back, we're going to take a look at these 2 problems.